All right, this is an introduction to the kinematic equations. What are the kinematic equations? Well, they're equations for the description and prediction of motion, where time is something that is value, starting position, position at time t, which we'll call final position, starting velocity, velocity at time t, which we'll call final velocity, and acceleration. Those are all our motion quantities. Now, I'm going to reduce this a little bit. I'm going to combine these two. If we put those together, we know that the final position minus the initial position is equal to displacement. And with a motion problem, usually you know one or the other of these. So if we know displacement, that's usually a good quantity to know. So we're going to replace initial position and final position with delta x. And we'll consider this set of quantities to be the things we are concerned about when describing or predicting motion. The first kinematic equation you actually already know. For an object that has uniform accelerated motion with a velocity at time 0 and a final velocity at time t, the equation of this relationship is the final velocity equals the acceleration of the object times time plus the initial velocity. And this is just substituting in values for a straight line, where the slope of that VT graph is the acceleration, the y-intercept is the velocity at time 0, and instead of x we have t, and instead of y we have velocity. And now for the second kinematic. Consider this object with uniform accelerated motion, starting velocity v0 and velocity vf at time equals t. What's the average velocity of this object? Well, if it starts at this velocity, increases uniformly to that, it's going to be right in the middle. For instance, if this object starts at a velocity of 4 and gets up to a velocity of 10, the average velocity in the middle would be 10 plus 4 divided by 2, which would be 14 divided by 2, or 7, which is right in the middle there. Therefore, in general, the average velocity is this: v0 plus vf divided by 2. And again, that equals average velocity. Now, that's not the second kinematic equation. Wait. We're going to get there with a substitution. So you'll remember this from constant velocity, that an object's displacement equals its average velocity times the time that it's in motion. If we substitute in average velocity for the expression we were just looking at, you get this equation where this quantity here is really equal to the average velocity. We're just substituting that in. This is the second kinematic equation. Now the third kinematic equation. Consider an object that is accelerating uniformly with an initial velocity v0 and a velocity at time t vf. The displacement of this object is equal to the area under the curve, under the line. And this area is really that rectangle area there plus the triangle part of the area. Rectangle area is just going to be v0 times t, and the triangle area is going to be this height here, which is really the change in velocity, times the base t, divided by 2 because it's a triangle. And we have this expression for the displacement of this object, this motion. But we're going to make a substitution now. We're going to substitute in for delta v there. This object, acceleration equals the change in velocity divided by t. If we rearrange this for delta v equals the acceleration of the object times time. So we'll substitute this product in for delta v. And here's that substitution. Delta v is equal to a times t, and a final version of this equation would be this. So this is kinematic equation number 3. And now our fourth kinematic equation. If you're paying attention, you'll recognize this as kinematic equation number 2. And we're going to start here and make a substitution to get our fourth equation. Recall from equation 3 this object's motion and this expression for change in velocity. If we rearrange this to solve for time, we'd have time equals change in velocity divided by acceleration. And if we expand this, change in velocity can be written as something's final velocity minus its initial velocity. So that's delta v, and then just leave acceleration in there. So we'll use this right now. So we'll substitute what I have here in green, vf minus v0 over 2 in for t. And I'm also going to pull this 2 out from here and multiply by a half instead. All right, this correction. Caught it just in time. Let's substitute in this expression for t. That was not a 2, that should be an a. That is what t is equal to. And we're going to substitute that in and pull the 2 out to get this. And I actually want to take care of this a, and I can also write this mathematical expression this way. And full advanced math here, but we need to multiply things. Multiply this times that times that, and we get this. Which this product becomes this, and this product right here becomes that, and that's just v0 vf minus v0 vf. So that all goes away. We're not done yet. Those two take care of themselves, but now we have to multiply the inside and the outside times each other, and so this is going to be vf squared, and this times that is going to be minus v0 squared. So that is the result of multiplying these two quantities together, leaving this, which I want to simplify to be this, which is usually written a little differently. If we multiply both sides by 2a, goes away over here, and I have 2a times delta x equals vf squared minus v0 squared, and now add v0 squared to both sides, leaves this final equation, which is the fourth kinematic equation. And this is the fourth kinematic equation. And here are the 4 kinematic equations all together. Now you'll notice we have our 5 quantities that we cared about. These 4 equations are comprised of these 5 motion quantities. And if you look carefully at each one, you'll notice from each kinematic equation, one of these quantities is missing, but the other 4 are there. Can you do it? First equation is missing delta x. The second equation is missing acceleration. The third equation is missing final velocity. And the last equation is missing time. These equations all came from velocity versus time graphical relationships and some clever substitution so that we could arrive at a set that has such a nice spread of use of those 5 quantities. So when it comes to problem solving, you can use graphical means, as we've done already, or rely on the kinematic equations and find a relationship here, an equation in which you know 3 of the quantities, and you can solve for the one you don't know. You may need to solve for initial velocity first using one equation, use it in another equation. These equations are very handy for predicting motion and solving for unknowns.